And then here we will discuss how much work we can do using electric circuits. And first we'll discuss electric power, which is shown on every electric appliance. Take a look at the figure on the right. It is a typical sticker you can easily find on any electric appliance, and it shows this number, which is the electric power. Okay, so what is this electric power? In order to understand it, let's think about it this way. The reason why you buy these electric appliances is to perform work for you, and then they do work by using this electrostatic potential energy supplied by battery or sometimes from electrical outlet on the wall, right? And the amount of work done by this machine is in fact equal, of course, to the amount of the electrostatic potential energy supplied by the source. And how do we calculate it? Let's calculate the infinitesimally small amount of work for a certain period of time is of course equal to the potential supplied multiplied by the change of charges, just playing a role of test charge, of course. And then this infinitesimal change in charge is of course equal to the current multiplied by this infinitesimally small period of time, right? This is what we all have learned. And then the electric power you have to calculate is defined as the rate of electrical energy transfer per unit time from the source to the device, all right? And whenever we use the word rate, what we mean is that the change of something per given time. So therefore, the electrical power, which is a rate of electrical energy transfer, we don't even have to say unit time, but explicitly we said unit time. And then how do we calculate is this? So P is equal to the time derivative of the energy, of course. And then we have seen what this in the above equation, du is now equal to v dq. So therefore, assuming that v is not changing very much for this infinitesimally small period of time, now dq divided by dt will be the current. So therefore, finally, we get the relation that electric power is in fact equal to the product between the current and then the potential difference. Okay. And then this is a general equation, so it is true for any kind of electrical energy transfer. So whether you have a heater like this, or whether you have a fan or television or radio, smartphone, anything, the electric power can be calculated by the amount of current flowing multiplied by the potential difference. Okay. And then what is the SI unit? SI unit, we have to divide energy by time, so therefore joule per sec. And then we call this watt, and then probably you remember the name James Watt from the Industrial Revolution. So therefore, okay, this watt comes from his name. And then we have just seen that power is equal to current multiplied by the potential. So therefore, joule per sec actually becomes equivalent to the volt multiplied by ampere. Okay, these two are the same. And then one important thing to mention. Okay, in the case of resistive heating, we may calculate power consumption using the alternative equations like these two here. And how did we get this? Remember from the Ohm's law, V equals I, say R, right? So if you insert V into the above equation, then you will get I square R. And if you insert I to the above equation, you will get V squared divided by R. Okay. But remember, these two equations, you may use this for calculating the power consumption of the heater like this, but you cannot use this in the case of, say, smartphone, or you cannot use this for television or any kind of things that do not use resistive heating. So this is only for heating appliances. Okay, and then if you remember what we have seen in this previous simulated experiment in the beginning part of this lecture, you remember when we increase the current, the color changes, right? Do you remember that? And then the color change represented the increase of the temperature. And then the reason was because when you increase this current, then the amount of amount of energy consumption, power consumption will increase, and it will go into the thermal energy. So that was the reason why the temperature increased when the amount of current increased. Okay, and then one more thing. And then, okay, we have calculated so far the power, which is the energy per time. So therefore, the total amount of work done over a certain period of time now can be calculated by integrating power with time. And of course, P is IV. So therefore, if if the current and voltage are constant, then you can simply multiply it by the period of time. But if they are not constant, then you have to perform integration. Okay. And then, okay, one last word. There are many interesting things here. What is the SI unit of work? Of course, a unit has the same dimension as the energy. And of course, you must know that the SI unit of work is joule, of course. But then sometimes in daily life, we often use a different unit, which is watt hours. So simply understanding that work is equal to power multiplied by time, we use their units directly, and hours is of course 60 minutes multiplied by 60 seconds. And take a look at the figure here. This is the electric power meter that every home has. And then the number here is using the unit kilowatt hours, right? So therefore, this is 1,000 times the watt hours. Now, why are we using this? This is because this unit is more intuitive. We know that whenever you buy electric appliance, it tells you how much power in watt it will be consuming. And then if you use this machine for several hours, then you can easily calculate how much watt hours you have used. Okay, that is the reason why this non-SI unit is very often used in daily life. Okay, this is the last slide before summary, and no more equations, so please relax. Here we will discuss what are the other types of conducting materials. Well, typically for wires we use metals like copper, but there are other types of materials we use for conduction. Okay, and well, resistors may be some of these, and it's very difficult to tell you what resistors are because there are so many different types. Okay, and instead something you have to know is semiconductors. I think semiconductors are very popular. So you think you know something about semiconductors, okay? In fact, semiconductors are not in fact conductors. They are insulators with relatively large conductivity. So let's try to compare three materials. First, copper, which is a typical metal, and this is a silicon, which is a typical semiconductor, and glass is the typical insulator. You can see the resistivity. Okay, resistivity of copper is very small. It's in the range of 10 to the power of minus 8 ohm meter. And in contrast, the glass has a very large resistivity, up to 10 to the power of 15. And then silicon is actually somewhere in between, 10 to the power of 3. Okay, and then it actually, one of the most important factors is that how much charge density or how much charge carriers are there. And then you can see how different they are. Okay, and then in fact, I think you can recognize these figures. This is something you will easily see inside your computers or any digital machines. These semiconductors, people typically call these semiconductors, but they are not semiconductors. They are devices made of semiconductors, and semiconductors are actually inside the box, and then what you see is just plastic cases. So these are semiconductor devices, not semiconductors. And then why is semiconductor so useful? If anybody asks you why is semiconductor so useful, while the semiconductor simply means a bad insulator, right? And the reason is because whenever you want to form a circuit, you want to have a conductor and insulator in order to make the current to flow to a certain direction. But then if you use a semiconductor, you can control it, because the property of semiconductor is somewhere between insulator and metal. You can modify its properties and do some very clever tricks, and then you can control the property in such a way that sometimes it works like a metal, sometimes it works like an insulator. Yeah, that's the basic idea. And then, of course, I have no time to explain it in detail, but later probably you will have some chance to learn more, okay? And there is another very, very interesting type of conducting material, which is called superconductors. So superconductors are materials that show zero resistivity at low temperatures, okay? This is a very difficult topic, so we will not go into it. Finally, let's make a summary. Okay, from this lecture, you have learned how electric current is related to electric charge, and the junction rule for electric current, which is related to the conservation of charges, and how to define resistance, resistivity, and also Ohm's law, and how to calculate power and work done by electricity. Okay, please make sure you understood all of these. And in the next lecture, next online lecture, we will study these things. Okay, and I will see you on Thursday. Okay, goodbye.